Good morning, everyone. So today we done class 5 of design of cooling systems. So first we'll see what we saw in last class. In last class, we had a small recap, which included uh, basically again going back to the introduction of what this course basically. So design of cooling systems. We made sure that uh, we'll work on MM1 systems per unit. So you have an arrival process and a departure process and a service process. So you want to control either the arrival process or the service process so that you have some requirements of the departures which we want are met. So uh, what we try to do is we try to formulate a machine problem so that the you minimize your delay or you minimize your service provider or some other things such that some of the constraints are right. So the assumption that we have taken at the arrival is a Poisson distribution with parameter lambda. The service times are exponentially distributed. The arrivals and service are independent of each other. The arrival times and the service times are independent of each other. And in the recap, we saw that. So first, what we did was we took a model. We fixed what the service arrival rate is, and we tried to find what the service rate is based on the cost function that we designed, which uh, minimized service plus waiting times. We found the waiting time equation for the M1Q. Next, what we saw was we fixed the s- service rate, and then we decided what the arrival rate should be so that the waiting time and the number of customer that has been served uh, is maximized. Right? The waiting time is minimized and you getting served is maximized. You have a reward for you getting served. So that is maximized. Right. Next, what we saw was in the arrival setting, when we are trying to find what is the optimal arrival rate. So we're trying to find what the optimal arrival rate is. The choice with the major key factors. One is each and every individual customer or a third party or the service provider. So basically, what happens when the service provider tries to take the decision, what he'll do is he will. So suppose your rate is lambda, your arrival rate, right? So he knows that the arrival rate is lambda, but he wants lambda prime so that the requirement is met and lambda prime is less than lambda, right? So what he'll do is with some probability, he'll pick out customers so that the arrival rate that happens is lambda prime. Now, what this does is, mm, so this is a social versus individual case which we saw. Where social case means that there is a third person who looks at the whole people of whole customers or whole jobs that have come to get service from this type of queuing system. He makes a decision so that the average waiting time and the total number of customers that have been served is optimized. Right? But if you look at each individual customer takes the decision, then what happens is uh, each individual customer will try to just maximize his own thing rather than the other parties. So we saw the inequality where person will always be recognized with the individual decisions that they have made. Right? So in the last class we saw both the optimal, both the irrelevant and service advantage. So both are the decision inputs. And then we defined a cost function both your mu and lambda decision variables and we saw that. So first, what would we see was okay. We saw that let us exclude 0.05 constant point, which is not good, is discontinuous, or it's not good. The function is not good, and then we did the first order conditions and just came up with solutions to it. What we saw was when we took the solution, the optimal solution by solving first order necessary conditions, you see that the cost function is performing worse than 0.0. Now, what does that mean is uh, by serving something, you're actually worse than not serving anything. So, to make sure where we went wrong, we checked out whether the cost function that we have designed is actually congruent concave or convex. So if you're maximizing, it's concave. If you're minimizing, it's convex. Right. So we saw that it is not jointly concave in lambda n. Right. Since it is not jointly concave, uh, the first order conditions are just necessary. So they won't be your minima. You can't say anything about it. So these are some of the problems that we face while designing optimal systems. You choose your decision variables. You, you formulate your cost function. You solve the optimization problem. You come up with a solution, but that solution may not be a optimal minima maxima because is the formulation. The formulation I've done is non-convex formulation, so you have to do something else, right? Okay, so today we will start with optimal arrival rates of. Two classes. So suppose we have an MM1Q, which has two classes. So you have an MM1Q, which has two classes of customers. The service rate mu, this is fixed. But the arrival rates of the two classes are lambda 1 and lambda 2. Now lambda 1 and lambda 2 are the decision variables. Customers are served in the order of their arrival, so the scheduling policy is FIFO. This has not changed. So the expected steady state waiting time is for both the classes. So expected waiting time. So now if I look this equivalently as I can see this as a queue with arrivals lambda 1 plus lambda 2, right? Because this is equal. The expected waiting time W is equal to minus lambda plus lambda. Uh, so so the steady state waiting time in the system uh, as a function is W lambda 1 and lambda 2, which I can also call as lambda, where lambda is lambda 1 plus lambda 2, and lambda is less than mu for stability reasons. Yeah. So uh, now we shall assume a reward cost model in the same way that we did in the previous section. But here we'll have class dependent awards and cost and waiting cost. So what does this mean is there is a reward RI for entering customer of class I, and HI is the waiting cost, right? The objective is to maximize the steady state expected net benefit per unit time. So you have max lambda comma lambda 1 comma lambda 2 b lambda 1 comma lambda 2 equal to R1 lambda 1 plus R2 lambda 2 minus lambda 1 H1 minus lambda 2 H2 W lambda. Okay, but you have a constraint here. That constraint is lambda 1 plus lambda 2 is equal to lambda, and both lambda 1 and lambda 2 are greater than or equal to 0. So here you have R1 reward for serving customer of class R1, you have R2 reward for serving customer of class R2, and these are your waiting costs, right? So H1 is the waiting cost for um, so, any level of class 1. H2 is the waiting cost for any level of class 2. Similarly, as we have seen in the single class model, it, if all rewards and costs are given to the customer, then a solution lambda 1s comma lambda 2s will be socially optimal, right? So what we're doing is we are splitting the problem into two problems. So the first problem is optimal arrival rate lambda 1 and optimal arrival rate lambda 2. And now the optimal that we saw here is lambda 1s, and the optimal that we saw here is lambda 2s. So you just say that lambda 1s comma lambda 2s is a solution which is socially optimal, right? In the sense of maximizing the aggregate net benefit that as a collective to all the customers, you see. So basically what is happening here is some third person is making the decision on behalf of the customers, right? And if yeah, if potential customers of class I arrive according to process with mean rate lambda I, so capital lambda I, which is greater than or equal to mu, then what you do is you allocate lambda is by lambda I. This is your probability AS. This is your allocation probability. This is your allocation probability. Okay. So you have your allocation probability. Uh, this is one method to do it. So we'll try also using the Piketty conditions. So first we'll try to find the derivative of this with respect to lambda 1. So your cost function lambda 1 comma lambda 2 is R1 lambda plus R2 lambda 2 minus lambda 1 H1 plus lambda 2 H2 W. Okay. Okay. So if we found derivative, then you get R1 minus H1 W lambda minus lambda 1 H1 W prime lambda, right? Oh, sorry. Plus lambda 2 H2 W lambda, W prime lambda. Because lambda is a function here, so you use the U unit. And this is equal to 0. So from this we have H1 W lambda minus lambda 1 H1 plus lambda 2 H2 W hat lambda W prime lambda, or the derivative of W with respect to lambda, is equal to R1, right? Similarly, if you do it with respect to lambda 2, you get R2 minus H2 W lambda minus lambda 1 H1 plus lambda 2 H2. This remains same. So this term remains same. And similarly, like H2W lambda minus lambda 1 H1 plus lambda 2 H2 W prime lambda equal to R, right? So basically, what you get is you get the equations R equal to HI W lambda plus delta, where I'll call delta equal to lambda 1 H1 plus lambda 2 H2 prime lambda. And so you will also have lambda 1 greater than 0. And Ri is less than or equal to inside W lambda plus delta lambda equal to 0. Okay. So you'll have these both cases because and we also have the constraint that lambda equal to lambda plus lambda. Now consider the system from the perspective of individual optimization. So social optimization, we saw that lambda 1 plus lambda plus is an optimal. So now we consider this problem from the perspective of the individual optimization. Right? So the customer is so how this comes into place. Suppose a fixed arbitral delta, this delta is the fixed arbitral is charged to each entry customer. Each customer of Plaza takes W lambda as given and choose the probability of German to maximize. So when does he maximize? AI, it's the probability of health class by Germany. Out of max which I W lambda plus delta plus 1 minus A into 0. So 1 minus A is him not joining. So this is the probability of him not joining. This is he has not joined, so reward is 0. This is the reward if he had joined. This is probability of him joining. And since AI is a probability, it will belong to the interval 0. So in other words, the class I customer who joins receives the net benefit RI minus HI double lambda minus the toll that he has to pay delta to use the facility. A customer who refuses to join or who walks receives or pays nothing. Right? So there is no reward, there is no cost. Then it is easy to see that the arrival rates. So this is this was I equal to AI into LI which satisfy either this or this equation. So I'll call this it satisfy with that A and B will be individual happen. Remember the for any given two, so for every given two, the solution to one A and B is a Nash equilibrium. Okay. So similarly, we saw in the single case of arrival class, socially optimal toll is just the external effect. As the marginal increase in the total delay cost incurred as a result of marginal increase in the flow. So because in the in the individually optimal, because more customers want to join the queue because they'll get a reward for it. Um, so the social optimal toll takes into account that more individual customers joining will actually increase the flow, which will actually increase the service, right? By charging the socially optimal toll. So what the system operator can do is can induce individually optimizing customers to behave in a socially optimal, thereby making the Nash equilibrium coincide with the socially optimal allocation of lambda 1s, lambda 2s, lambda s, where lambda is equal to lambda 1s plus lambda 2s. Okay. So now let us just tweak the problem a little bit and find explicit expressions. And using the explicit expression for W lambda, we'll try to find a socially optimal solution of the two flow case. So we are trying to maximize reward. We have this at R1, R2. right? We are maximizing R1 lambda 1 minus H1 lambda 1 by u minus lambda 1 minus lambda 2 plus R2 lambda 2 minus H2 lambda 2 by mu minus lambda 1 minus lambda 2. So this is the reward of reward seen by arrivals of class 1, and this is the reward seen by arrivals of class 2. The constraints remains the same, lambda equal to lambda 1 plus lambda 2, and lambda 1 and lambda 2 are greater than or equal to 0. So what we'll do is we'll make some assumptions here. So assumptions are, we'll assume that mu equal to 1, right? If we solve for mu equal to 1, then replacing uh, so what we are doing is we're measuring flows in units of fraction of surface rate, right? So if I say it is 1, then it means that I'm using the whole surface and so on. Okay, and I'll define some terms. A equal to R1 by H1, B equal to R2 by H2, C equal to H1 by H2. So now this problem, this, let me call it C. Problem C is now modified as max lambda 1 comma lambda 2 C into A lambda 1 minus lambda 1 by 1 minus lambda 1 minus lambda 2 plus B lambda 2 minus lambda 2 by 1 minus lambda 1 minus lambda 2. Okay. The constant still remain lambda 1 plus lambda 2, but now it is less than 1 because lambda plus 1 is less than 1, right? And lambda 1 and lambda 2 are greater than equal to 0. Okay. So for an interior optimal solution, these two, this must be A must be for internally optimal solution. A must be satisfied. Okay, so when I say A must be satisfied, let us write down that A equation Ri equal to. Oh, we can just take the derivative of this first lambda I once more and equal it to 0 and see what happens, right? So if we take the derivative of this with respect to lambda 1, so we are taking the derivative of this with respect to lambda 1, we get Ca minus 1 by 1 minus lambda 1 minus lambda 2 plus lambda minus lambda 1 by minus this is equal to 0. Similarly, if we take with respect to lambda 2, we have C lambda 1 by square plus B plus lambda 2. So we put this as minus 1 by 1 minus lambda 1 minus lambda 2 plus lambda 2 by 1 minus lambda 1 minus lambda 2 whole square. This is equal to 0. Okay. So now we have to solve for lambda 1 and lambda 2. So this term is full of this term is full of lambda 1 lambda 2. This term is full of lambda 1. We'll keep them both on one side and we'll see what happens. C equal to 1 by 1 minus lambda 1 minus lambda 2 plus lambda 1 by minus lambda 1 minus lambda 2 whole square minus lambda 2 by 1 minus lambda 1 minus lambda 2 whole square. Right. Similarly, B equal to 1 by 1 minus lambda 1 minus lambda 2 plus lambda 2 by 1 minus lambda 1 minus lambda 2 whole square minus C lambda 1 by 1 minus lambda 1 minus whole square. As you can see here, in both the cases, 1 minus lambda 1 by lambda 2 is common. Okay, 1 minus lambda 1 minus lambda 2 plus lambda 1 minus lambda 2. So, lambda 1 lambda 1 cancels, and you have 1 minus 2 lambda 2 by 1 minus lambda 1 minus lambda 2 whole square. So, see, similarly, B is equal to, so the same thing here, 1 minus lambda 1 minus lambda 2 whole square. Yeah. And you have 1 minus lambda 1 minus lambda 2 plus lambda 2 minus C lambda 1, right? So here you have lambda 2 cancel, and you have 1 minus C plus 1 lambda 1 by 1 minus lambda 2 whole square. Okay, from these two, you have 1 minus 2 lambda 2 by CA equal to 1 minus C plus 1 lambda 1 by B. Mm, We also have CA by 1 minus 2 lambda equal to B by 1 minus C plus 1 lambda. Right? CA this is 1. From here, I think I can get it in terms of lambda 2. So lambda 2 is equal to 1 minus 2 lambda 2 equal to CA into 1 minus C plus 1 lambda 1 by V. Right? 1 minus CA this is lambda 2. Right? To be B minus CA. But I need to remove this lambda 1. Lambda 1 needs to be removed. From same equation, we can get lambda 1 in terms of lambda 2 and substitute it here, and then we get okay. So lambda 1 in terms of lambda 2, you have lambda 1 equal to B into 1 minus 2 lambda 2 by CA. One minus B into 1 minus 2 lambda 2 by CA. C plus 1 by C plus 1. This is lambda. CA minus B into 1 minus 2 lambda 2 by CA into C plus 1. If we substitute this here, we get lambda 2 is equal to B minus CA 1 minus C plus 1 into CA minus B into 1 minus 2 lambda 2 by CA into C plus 1. C plus 1, C plus 1 cancels. By 2B. I'm going to take that side of it. B minus CA into CA minus CA plus B into 1 minus 2 lambda 2 by CA by 2B. So lambda 2 equal to B minus C minus C minus C minus into 1 minus 2 lambda 2 by 2B. So lambda 2 is equal to 1 by 2 minus 1 by 2 into 1 minus 2 lambda 2 Yeah. So finally, what we get is we get two unique solutions. So I'll let this the unique solutions now. The unique solutions are b into c minus 1 by ca minus b whole square minus 1 by c minus 1, and lambda 2 is c by c minus 1 minus ca into c minus 1 by ca minus b whole square. So now from this we can see that lambda 1 tilde and lambda 2 tilde, which is the optimal, is an interior point because lambda 1 tilde greater than 0, lambda 2 tilde greater than 0, and lambda 1 plus lambda 2. If you do lambda 1 plus lambda 2, then you get that is less than 1, right? Uh, so this is an interior point if it satisfies the following conditions. The conditions are b is greater than a is greater than 1, c greater than b minus 1 by a minus 1, and a is less than ca minus b whole square by c minus 1 whole square less than b, right? So how can we see that? How do we get this? Is we'll add these two, right? So first one by tilde is equal to b c minus 1 by ca minus b whole square minus 1 by c minus 1 plus c by c minus 1 ca minus c minus 1 by ca minus 1 whole square. So we have b c minus 1 minus c minus 1 by ca minus b whole square minus plus c minus 1 by. C minus 1 by C minus B plus 1. So this should be less than or equal to 3 by C minus 1 is less than C plus B. B minus C. Oh, and you also have, you know, so okay, what does it mean to say that this is an integral quantity? We have lambda 1 greater than 0, lambda 2 greater than 0, and lambda 1 plus lambda 2 greater than 1, right? So basically, yeah. So you need this is the third condition that I've written, but you also need to satisfy lambda 1 greater than 0, lambda 2 greater than 0. So for lambda 1 greater than 0, we'll get bc minus 1 by ca minus b whole square is greater than Okay, so from this condition, lambda 1 greater than 0, we have gotten CA minus B whole square by C minus 1 whole square less than B. So this condition, right? Next is lambda 2 greater than 0. So lambda 2 greater than 0, we have C by C minus 1 greater than CA into C minus 1 by CA minus B whole square. Okay. A is less than CA minus B whole square by C minus 1 whole square. So we have from the this is the third condition, second part. From this we have third condition, first part. Right. So these two we have done. Now from this lambda 1 plus lambda 2 is less than 1. From that condition we get this, which we can write it as C into 1 minus A less than B plus 1. So C is less than B plus 1 by 1 minus A. So, oh, sorry. So what we get from here is C minus 1 by CA minus B. It should be less than 0. If it is less than 0, then this will be, so which implies C minus 1 is less than CA minus B, right? And you take B this side, B minus 1 less than equal to C into A minus 1. So C is greater than B minus 1 by A minus 1. Yeah, this is what you get. Okay, so we have gotten this. And the last one, B is greater than A is greater than 1. Yeah, so to satisfy that, to see that the optimal point that we have found here is in fact interior point. It needs to satisfy these three conditions, which we have shown from the equivalence of the interior conditions points that it needs to satisfy. Okay, so for an MM1 system, the parameter satisfies this condition. We have established that the first order optimality conditions have a unique integral function, right? That is like a detail. This results can us to conclude that this solution is indeed optimal. But in the previous section, where we saw that when we are designing both the Arrow and optimal solution, the unique integral point solution to the optimal solution, optimal conditions turn out to be non-optimal. So the question still remains if the non-integral point solution to the frequency conditions and whether one of those could yield a higher value of objective function than what the integral point method has given, right? So and another way of posing this problem is the KKT condition sufficient and necessary for an optimal solution, optimal probability solution? So we'll return to the original, we'll return back to the solution, optimal problem. Optimal problem is B lambda 1 comma lambda 2. This is R1 lambda 1 plus R2 lambda 2 minus F lambda 1 comma lambda 2, right? Where F lambda 1 comma lambda 2 is lambda 1 H1 plus lambda 2 H2, creating lambda 1 plus lambda 2. Okay. So F lambda 1 comma lambda 2 is total delay cost per unit time expressed as a function of lambda 1 and lambda 2. The KKT conditions will be sufficient for social optimality if B lambda 1 comma lambda 2 is jointly concave. That is what we know in lambda 1 comma lambda. This is true only if F, because these two are linear or affine function of lambda 1, lambda 2. So this is basically both concave and convex. So we need to show that this is jointly convex in lambda 1 comma lambda 2. Okay, so we'll try to show that f of lambda 1 comma lambda 2 is convex in this convex of lambda. You can see from this equation, you can see that because we've done this before, this is convex in lambda 1 and also convex in lambda 2, right? But we'll calculate actually the delta. Delta is rho square f by rho lambda 1 square, rho square f by rho lambda 2 square minus rho square f by rho lambda 1 rho lambda 2 whole square. Right. Delta equal to minus h1 minus h2 w prime given plus 1 whole square. This is strictly negative unless h1 equal to h2. Therefore, f of lambda 1 comma lambda 2 is genuinely not jointly convex, but the conditions for joint convexity fail at every point in the feasible case. So if the customer class are heterogeneous, that is if h1 is not equal to h2, it follows that lambda b lambda 1 lambda 2 fails to do jointly concave unless h1 equal to h2, right? So a small note is the functional form that we have seen here in the cost function in the demonstration of a non-convexity. The only properties that we used are the delay w lambda for each customer that is increasing convex and differentiable function of the sum of the flows. Now the delay cost per unit time for each class I is a product of the flow lambda, and the delay cost per customer is hi into w lambda. All these properties are weak and hold for many queen models, not just for MM1 case. So if we go and change the case where it's not MM1, right, non-convexity will be encountered in most of the cases, right? MM1 will be simplest of the cases. For design with more than one decision variance, the non-concavity of the function b lambda 1 lambda 2 so uh, makes us believe that only KKT conditions might not be sufficient for an optimal allocation, right? Interior point solution to this condition, such as one found in the previous section, might not be optimal. Now, okay, now what we do is we observe the solution that is on the interior, is not on the interior, but lies on the boundary of the solution. So that satisfy lambda 1 plus lambda 2 equal to lambda, right? So we have R1 minus H1 W lambda is equal to R2 minus H2 W. Along this line, both the total flow lambda and the net benefit B lambda 1 and lambda 2 are constant. So B lambda 1 comma lambda 2 is equal to 2. Let us say that this is true. The two extreme points on this line, namely, we have this 0 and lambda and 0. So this is lambda 1, so lambda 1, lambda 2. So this is a line. So x plus y is equal to c. Okay. Shade the net benefit that b lambda comma 0 is equal to b 0 comma lambda is equal to 2. But b lambda comma 0 is less than or equal to b lambda 1 star comma 0. And similarly, b 0 comma lambda is less than or equal to b 0 comma lambda 2 star. Where lambda I star is the optimal flow allocation to class I when only class I receives positive flow. So what we see here is the integral solution to the first order condition is dominated by both optimal single class allocations. In other words, the system achieves at least as great a net benefit by allocating all flow to a single class regardless of which class. Then by using an integral allocation, which we have derived using the first order condition, right? Which does not make sense, but okay, let's look into the math. Our next observation, we'll deal with the external effects, congestion tolls, and equilibrium properties, right? First, we see that charging user a toll delta per unit flow equal to the external effect, that is the delta that we have defined earlier. So, toll delta equal to lambda 1 h1 plus lambda 2 h2 w prime lambda 1 plus lambda 2 makes the solution that we have found lambda 1 tilde and lambda 2 tilde Nash equilibrium for individual optimizing customers. No customers of either class is an incentive to deviate from this allocation, assuming that all of the customers make no change. Thus, that is what a Nash equilibrium basically means. Even by charging the correct toll, we cannot be certain that the customers will be directed to the socially optimal flow allocation. Rather, the resulting allocation, even though it's a Nash equilibrium, may be dominated by both of the optimal single class allocations. Right? Thus, we have a dramatic summation of pitfalls of marginal cost pricing, that is pricing based on first order optimal conditions. When the customer classes are heterogeneous, they are sensitive to the congestion. So I'll just give a small example. So if A equal to 4, B equal to 9, and C equal to 4, right? Where A equal to R1 by H1, P equal to R2 by H2, C equal to H1 by H2, right? Then what we see is lambda 1 tilde equal to 0.218, lambda 2 tilde equal to 0.354. Okay, and if you put this in cost function, lambda 1 tilde, lambda 2 tilde, this is 3.81. But if you do the socially optimal at the first flow and then nothing for the second, then you get 4. And similarly, B of 0 comma lambda 2s, this is 4. Right? So basically, doing nothing to one flow and doing optimal to one flow is better than the interior point that we have found out is in the conditions is not as good, right? Okay, so that is it for today's class. In the next class, we will see when we have parallel queues. So we have um, 10 independent MM1 queues with service rates mu j and arrival rates lambda j. Mu j are fixed and lambda j are the design variables. So we want to minimize the expected number of customers in the system, right? Yeah, we'll formulate the optimization value and we'll see. Yes.